Okay, hello everyone. We are going to continue our brief discussion on flight dynamics, flight mechanics, and flight dynamics in general. Today we will learn a little bit about landing and takeoff, and also the engine controls, and maybe a little bit of stall conditions. And for the next lecture, which will be posted on Monday, you will learn about the X-plane, which is the flight simulator we are going to use in the lab, and also you will learn about the playmaker, which is the tool you are going to use to modify the aircraft. So let's start with the landing and takeoff. To be airborne, the lift produced by the airplane must be at least equal to the weight of airplane. Otherwise, your aircraft won't be able to be airborne, of course, because the main force that is keeping your airplane down is the weight of airplane, and the lift you're producing, which is going to counteract the weight, must be equal or greater than the weight. Okay, and the velocity of the airplane must be equal or greater than its stalling speed. Okay. When an airplane comes to land, the lift produced by it again must be nearly equal to the landing weight. Okay. The reason for this is the fact that you want to be able to control the aircraft. So if during the landing the lift produced is smaller than the weight, you are not the one that is landing the aircraft. The aircraft weight is actually landing the aircraft. Your aircraft is falling down. It is not landing. Okay, so control is the main reason we wanna produce lift that is nearly equal to the landing weight. Okay. In the continuing discussion, we will learn a little bit about takeoff velocity and touchdown velocity and the touchdown distance and the takeoff distance and how they are all related to each other, and what are the different definitions that are used in the landing and takeoff analysis. You will see a more in-depth discussion about the landing and takeoff in your flight and orbital mechanics course, AESP 420, hopefully. But the science behind landing and takeoff is pretty simple. And this is something that you can do with a basic mechanics physics, essentially. Okay. You have to keep in mind that the takeoff distance is defined as the horizontal distance covered by an airplane from the start of the run until it climbs to a height equal to the screen height. Okay, and the screen height is actually an arbitrary height that we have chosen, and this has chosen to be as tall as a 5-story tall building, so essentially 15 meters. Okay, this is also true for the landing. The landing distance is the horizontal distance it takes to go from the screen height to the velocity zero condition, the full stop condition. Okay. So, as discussed before, the takeoff starts from here at v equals to 0. Then you have your first transition here from the ground run to the transition conditions, which is this part. So you will have the ground run here, and then the transition condition, and afterwards you will get to the climb condition until you have climbed up to 15 meters in height in the vertical direction. This distance is called the takeoff distance. Okay, and we will learn how to calculate the distance essentially using the velocities at each direction. So you have to know one of the variables here. You either have to know the velocity or you have to know the distances here to be able to calculate the other one. Okay, but before doing that, you have to keep in mind that this velocity is called v. Sorry, vt0. That's the initial takeoff velocity, if you will, the velocity at this point, as at the on-stick point, right? And the pilot has to has the wheel lift off, nose wheel lift off. So the nose wheel has to come off the ground using, and the pilot is controlled that using the stick, right? The pilot is essentially going to pull the stick a little towards him or herself, and that should happen when the velocity reaches 85% of the initial takeoff velocity, VT naught, essentially. And airplane will be airborne at the when the takeoff speed. When you do this, when the pilot does this, the airplane will be airborne when you reach the takeoff speed. Okay, the other thing that you have to keep in mind is that we have different types of airplanes. We have airplanes like this, where we have nose wheel, or airplanes like this, where we have tail wheel, right? They essentially their mechanism, their takeoff mechanism is a little bit different. As I said, mentioned here, when you reach this velocity, you have to move the nose up, pitch the nose up, essentially nose wheel up a little bit to be able to be airborne. But the table type airplanes essentially the tail wheel goes up itself, but because of the aerodynamic forces that are being applied on the wheel, and it will be airborne at the appropriate velocity. Okay, the same conditions apply to the touchdown and takeoff and the landing. Sorry. So you have the final approach distance. You have the flare distance, which is equal to the transition distance when you are taking off. We have an additional distance when the aircraft is floating, but it's not on the ground yet, right? So essentially it is on the ground, but it is not on the ground, meaning that the thrust and weight are basically equal and the aircraft is moving just, let's say, 1 millimeter above the ground, right? After the floating, we will have the touchdown, where the aircraft lands, and then we have the ground run S of G, which is going to be the bulk of the landing distance. And the landing distance, as mentioned earlier, the same as takeoff distance, is going to be this total distance. So from the screen height to velocity 0. Okay, so essentially it's basically the same thing as landing, just the other way around. Okay. So let's try to do a mathematical analysis of this. So if you go to, let's go to the landing takeoff thing. If you are dealing with this, okay, the forces that are being applied is the lift, weight, the normal ground force, the thrust, and drag, right? And you also have the friction force, like mu r. So we can write the force balance in the both directions, in the x direction or in the horizontal direction. You are moving in that direction before reaching this point, the transition point, the on-stick point, right? You are moving in that direction, so the acceleration is only happening in that direction. The weight, the mass of the aircraft is its weight divided by the gravitational acceleration. You have the friction that is acting against thrust, you have the drag that is acting against thrust, and you also have the thrust. So this is a very simple force balance that you can write for the aircraft that is going to take off in the X direction. Okay, in the Y direction, there is no movement in the Y direction yet. So we only have lift, the normal force, and the weight, right? So essentially your normal force and all of them is equals to 0. So your normal force must be equals to weight minus lift. Using this, you can actually find the acceleration, right? Because we have the normal force definition, we are going to replace this here and just move things around. This is the equation you are going to get. A is equal to T minus D minus mu multiplied by W minus L. And we can also use a definition of acceleration, which is dv over dt, multiply and divide by a ds, which is a differential of the path that is taken by the aircraft, and ds over dt itself is dv over ds. Okay, so we can have these two. Essentially, a is equals to b dv over ds, and a is equals to this. But the goal here, as I mentioned, is either to calculate the velocity or the distance, right? At this point here, we want to calculate the distance. So you rearrange all of these formulas. Like we have v dv ds equals to t minus d minus mu w minus l over w over g. Right? If you move the v dv to the other side, or ds to the other side and the rest of them to this side, this is what you are going to get. S is going to be equal to the integral from 0 to v1, which is the velocity at on stick points when the nozzle actually when the aircraft goes to the transition mode, and that's the velocity. This is the v1, that is the velocity. Then vdv over t minus d minus mu w minus l. Okay, so you simply can find the ground run using this formula. We can also do another analysis. We can try to find the ground run time. Essentially, to do so, we are going to use this part of the acceleration definition. Okay, using that, you can find the time it takes to get from here to here for a specific aircraft at a specific velocity. You can find it. Yeah, you can find that. Keep in mind that we are going to use constant coefficients of rolling friction. I'm sorry. For this case, depending on the type of surface you are working on, you are going to use different coefficients of rolling friction. So essentially, you may see this in a quiz later in the semester. You just have to make sure that you are comfortable with using these integrals and these problems, these equations in general, in your analysis. Okay, the transition distance can also be calculated. Here we are looking at this distance. We are going to ignore the elevation here because it is very small and can be neglected. Okay, so if you write the energy balance for your system, you are going to get that the forces you have in the x direction is the T thrust, S is the distance, force multiplied by distance is going to be your work essentially done by the system, right? And the same is for drag, and we are going to have the kinetic energy of the system on this side. That's 1/2 of m v squared, v2 squared minus v1 squared, right? So there should be a balance there. Okay. Using this equation, and if you have these velocities, you will be able to find the transition distance. Transition distance is going to be W, your weight, over the 2 multiplied by the gravitational acceleration. V squared over 2, v2 squared, sorry, minus v1 squared over t minus d. And the time of transition is going to be this distance over half of v1 over v2. So essentially what we do here to calculate the time is that since v1 and v2 are pretty close to each other, we are going to assume that the speed is uniform here. We are going to find the average, and just by dividing this velocity, just dividing the distance by velocity, you are going to get the time, right? So a lot of assumptions, a lot of approximations in the analysis of landing and takeoff. But even though we are making all of these assumptions in our analysis, we usually get good data and good results. Okay. And the third part of takeoff is the climb distance. The climb distance can be simply calculated by the screen height, which is 15 meters usually. Sometimes it is 30 meters, but you will be given the screen height, right? This is not something that you have to calculate yourself, right? It is just a definition, essentially. It is just an assumption, a given parameter. A screen height divided by the tangent of gamma, where gamma is the angle of climb, and we can calculate gamma using a very simple force balance in that direction and calculating the angle these forces are essentially taking, the thrust and drag and weight are having each other. Okay, so angle of climb can be calculated by taking the inverse of sine of t minus d over w. And the time of climb, so essentially the time it takes to go from here to here, can be calculated by this equation, screen height over vt multiplied by sine of gamma. Okay, let's go to engine control. So essentially when we talk about engine control, we are talking about the fact that the pilot should and must monitor and control the operation of the aircraft's power plant or engine, right? Controlling the aircraft or engine is one of the most important jobs of the pilot. You want to make sure that the aircraft is always airborne. You want to make sure that you are producing enough thrust for the aircraft to be to fly, essentially, right? And the pilots must be always aware of the situation of the engine. But what we do when we say we have to control the engine is essentially we control the flow of fuel and air into the engine, which controls the combustion that's going to happen, the thrust that is generated, right? To allow it to operate at its optimum efficiency over a wide range of speeds, altitudes, and temperature. And you have to keep in mind that different types of aircraft need different types of control, which we will discuss. They need different types of control philosophy. I'm not talking about the equipment itself, but the philosophy of controlling the aircraft, which we will talk about. We will talk about right here. So if you're dealing with a military aircraft, your pilot have to control the engine in a way that makes the aircraft operable in all around the world, especially on worldwide conditions. And it has to be able to operate in wide range of operating conditions, like low altitudes, high altitudes, in the mountains, snowy conditions, rainy conditions, or under the sun, a lot of different conditions. Because it is a military aircraft, it has to be durable, it has to be able to fly to different locations. And also the most important part is that it must be maneuverable. Right? Maneuverability is very, very important. You don't really care because you don't have any passengers other than the bombs that a military aircraft is carrying. There is no other passenger. And so you don't really care if your passengers don't feel well, right? They don't really care about the stability at that point. You just want to be able to maneuver as fast as possible. And civil aircraft, but when you're dealing with the civil aircraft and commercial airliners, you want to make sure that your aircraft is reliable, so your passengers remain safe as much as possible, and you want to make sure that it can operate during the long term and it doesn't use that much fuel. So you want to bring the cost down essentially. And you want to make sure that your aircraft is stable enough so to minimize the risk to your passengers essentially. There's also this concept that we have to be aware of. It's called the engine stall. I'm pretty sure you have learned about the airfoil stall, the wing stall in your aerodynamics. We will talk about it a little later in this lecture as well. But aside from wing stall, your engines can also stall. As you can see, we have a visualization of how engine stall goes essentially. Here we have the normal inlet airflow, the air is going in and reaching the compressors and so on and so forth, right? But when your engine has a stall, the flow of air inside is distorted, right? So essentially, the engine stall refers to the slowing or stopping of engine operation mid-flight. Okay, it can be caused by insufficient air or fuel supply, electrical or mechanical failures, or sudden increase of engine load. And it is a very important part of engine control because you want to make sure that your fuel supply or air supply is always sufficient. You want to make sure that you don't change the engine load suddenly, right? And electrical and mechanical failures are outside of pilot's control, but the maintenance have to always take care of those and keep those in mind. Okay. The next step is to talk about the instruments you use to control the engine. It is just a list of the instruments. I'm just going to go over them and read over them. There's no explanation, just have to be familiar with these. And these won't be a part of any exams or anything. I just wanted to make sure that I include these so you at least have heard about them. We have the master switch, which usually uh, is usually also called the battery master or alternator master, which essentially turns the engine on. We have the throttle, which controls the mass flow rate of air or the air-fuel mixture delivered to the cylinder. So the air-fuel mixture is in carbureted engine, and the same system is also used in cars, especially in the older cars, the fuel injection or the carburetors. Pretty sure you have heard about these words about cars, but we have the same system as far as the propeller aircraft goes, right? The aircraft that use an engine don't use a jet engine, don't use a jet. Okay. We also have the propeller control that adjusts the constant speed unit of the propeller. Okay, which also can in turn adjust the propeller pitch and regulates the engine load as necessary to maintain the RPM of the engine. There is also the mixture control, which sets the amount of fuel added to the intake airflow. And this is mostly used in the jet engines. We have the ignition switch that activates the magnets to send this high voltage output to the spark plugs for the ignition. We have the tachometer. It's a gauge that indicates the engine speed in RPM or percentage of maximum. We have the manifold pressure gauge, indicates the absolute pressure in the intake manifold. We have these two gauges in a car as well. We have the lubricant temperature gauge, which we don't have in a car, but you have to have it in a plane, right? That indicates the engine oil temperature. We have the lubricant pressure gauge, very obvious, right? We have the exhaust gas temperature gauge, or EGT. To brief, we have the cylinder head temperature gauge, and we have the carburetor heat control in the carburetor systems, of course, the older system. We also have the alternate air control, which controls the bypass of the air over the jet engines and fuel injected engines. And this is a schematic of the engine control system. You have the control system that reads the data from your feedback system and then changes the conditions of the aircraft, the engine, the power plant of the aircraft. Okay, and the pilot can also control the different things inside the engine using the gauges in front of him or her, and that's it for the engine controls. But as we have mentioned, we are going to use the Cessna 172, which is one of the most popular aircrafts in the world, one of the most popular personal aircraft, if you will. So not commercial, not military, just like if you want to go out and buy an aircraft, you probably will buy a Cessna 172. And we have to make sure that you are familiar with the gauges, because this is the aircraft you're going to use in the lab, right? There is something called the basic T, which are the most important gauges of the aircraft. 1, 2, 3, 4, and this is 5 essentially, right? And these look like a T when put beside each other. That's what they are called, the basic T. So your gauge number 1 controls the airspeed, or indicates the airspeed. It is an airspeed indicator. You read the airspeed using the pitot-static, and then it gives the speed to the gauge number 1. Gauge number 2 controls the altitude using the gyroscope. Number 3, gauge number 3 controls is the altimeter, and gives you the altitude using the pitot-static. Gauge number 4 here is the vertical, I'm sorry, it's the other way around. Gauge number 4 here is the vertical speed indicator, again with the pitot-static. Then we have the heading indicator, which is one of the basic T, gyroscope, and we also have the turn indicator number 6, which is also an important gauge, but it's not part of the basic T. That tells you about turn, whether your aircraft is straight or is turning or rolling, essentially. You have to keep in mind that there are other very important gauges in the modern aircraft, but these 4 are a carryover from the old aerospace industry, if you will, right? That the older generations, the earliest aircraft, the earliest modern aircrafts, if you will, only had these 4. Not only had these were the 4 main ones that the pilots could check and make decisions based on their conditions and situation. So let's talk about the different types of stall on airfoils and wings. I'm pretty sure you have seen this section of the lecture in your aerodynamics course, but we have to go over it anyways. Right? We have the leading edge stall, we have the trailing edge stall, and we have the something called the thin airfoil stall. So the leading edge stall happens when the flow suddenly separates from the leading edge, right? So the separation doesn't start from the back. It does not start from the back. Does not start from the back. All of the flow essentially separates from the leading edge to the trailing edge suddenly, right? It is a very sudden thing. It is characteristics. It is a characteristic of a relatively thin airfoil with thickness ratios between 10 and 16% of the chord length. Because of this sudden change, you will see a very sharp peak in the CL versus alpha plot, and it will follow a very rapid decrease because of this very sudden separation of the flow. Okay, but we also have the trailing edge stall, where the flow separation starts from the trailing edge. My pen doesn't work anymore. Okay. Where the flow separation starts from the trailing edge and then it moves gradually up towards the leading edge. Okay. It is a progressive and gradual movement of separation from the trailing edge to the leading edge. It is characteristics of a thicker airfoil. And the thin airfoil style, it happens in extremely thin airfoils, right? So the airfoil is so thin that you can just assume it's a flat plate, right? The thickness of the airfoil is essentially around 2% of the chord length, and the main reason behind this very sharp flow separation is the fact that your flow only sees essentially very sharp corners. So let's have a magnified view. What the flow, your airfoil may be something like this, right? But it is so thin that the upcoming flow sees this, right? So it sees very sharp corners. And because of that, you will get the thin airfoil stall conditions. So if you want to be able to compare the stall conditions, you will see that the leading edge stall, you will get a higher CL max, but then the stall conditions is more dramatic and there will be a very sharp increase. Whereas the trailing edge stall, you CL max won't be as high, but the decrease in the lift is not as dramatic and as drastic as the others. And the thin airfoil, of course, gets the lowest CL max. The main reason behind it is that the flow sees very sharp corners, and those trigger the flow separation much sooner than the other two conditions. Okay. So since we are doing this recording and I don't get any questions from you guys, I go very fast. But if you feel like that I have to pause a little bit, I have to try to explain things a little more, please let me know. At the end of the day, these lectures are geared toward your lab. So as long as you understand what's going on in the lab and you can figure out how to do the lab, you should be fine. But for the next lecture, we are going to talk about the software, the flight simulator you are going to use for lab 1 and lab 2, which is called X-Plane. And we will also talk about the plane maker, which is another software you are going to use to modify the aircraft. So essentially in your lab reports, these are the type of things that I want to get from you. I want to have CL versus alpha, CD versus alpha, the drag polar, CL versus CD, and also the coefficient, the lift to drag ratio versus angle of attack. And we're going to teach you how to fly the airplane essentially, and how to monitor the data, how to get an output of the data, and you should essentially be able to perform the lab without any problems. I guess that's it for today, and I'm gonna post this lecture on Wednesday morning. Let me know if you have any questions, and have a good weekend.